So in this video we're going to find the inverse Laplace transform of this function here, f of s. 3s squared plus 4s plus 21 divided by s cubed plus 3s squared plus 3s plus 9. Now that looks really complicated for us to take care of, so we're going to have to take this by a few steps at a time. Now first of all, looking at f of s, so if we break down f of s into p of s divided by q of s, p of s is of order 2 and q of s is of order 3. So therefore the limit of p of s divided by q of s as s approaches infinity, that equals 0. So therefore with this, what we're looking for is to try and break this down into some sort of fractions. Now s cubed plus 3s squared plus 3s plus 9, that's a cubic equation there that looks like we could perhaps do something with. So coefficient here is 1 and this one is 3, and then next to this we've got coefficient of 3 followed by coefficient of 9. Now each of these are increasing by threefold each time, so 1 and then 3 and then 3 and then 9. So let's break down our q of s. So q of s equals s cubed plus 3s squared plus 3s plus 9. Now if we do break these down into two parts, take an s squared out of this one, we're left with s plus 3. And then this one, if we take the 3 out, so we add 3, we're left with s plus 3. So we've got s plus 3 in both. So therefore this, we can break that down into s squared plus 3, hence these two, and then s plus 3. So that's what we've got so far. So now our f of s equals 3s squared plus 4s plus 21 over s squared plus 3 and s plus 3. So then we've got a chance now to try and find some way of breaking this up into two fractions. So partial fractions is definitely a possibility, but it still seems a long way off with what we've got going on here. So maybe there's more we can deal with here with our numerator p of s. So let's have a look at p of s. So p of s equals 3s squared plus 4s plus 21. Now can we get any of these out of this? Now if I have a look at s plus 3, I could possibly take an s plus 3 out of there because I've got 4s plus 21. Though if I take out 4 times s plus 3, that would leave me with 4 times s plus 3, that's going to be 4s plus 12. So let's just make a note of that. So 4, because we've got 4s, look at this s plus 3, s plus 3, that gives me 4s plus 12. Now if I subtract 4s plus 12 from this, so p of s minus 4s plus 12, that would then leave me with 3s squared, and I've got a 4s here, that's gone, and 12 from this, that's going to leave me with 9. So 3s squared plus 9. Now here I've got an s squared plus 3. Can I get s squared plus 3 out of this? Well, luckily our answer to this, if I just factor out the 3, I've got 3s squared plus 3. So therefore I can break this apart now. So my f of s, I can write that as 3 times s squared plus 3. And then I've got here 4s plus 12, so that's 4 times s plus 3. So add on to that 4 times s plus 3. So that's my p of s, breaking that down. And now if I divide that by my q of s, which I got here, s squared plus 3 and s plus 3. So now I can break my fractions apart. So I've got this one my numerator with this fraction, and then this one with this again. So now I can rewrite this as 3s squared plus 3 over s squared plus 3 s plus 3, and then add that, because I can break it apart as it's in the numerator, 4 times s plus 3, and then my whole denominator again. So now I've got s squared plus 3 s plus 3. So now I can start cancelling stuff out and leave me with two fractions. So s squared plus 3, they can both cancel out. And here I've got s plus 3 in both, so they will cancel out. So now I'm left with f of s equals 3 over s plus 3 plus 4 over s squared plus 3. Okay, now that is definitely something I can work with inverse Laplace transform. So I'm going to use that. So let's clear all this stuff off the board and start with this up the top, and let's start breaking it down into inverse Laplace. Okay, so now we've got all this up here on its own. So now we can try and find the inverse Laplace transform. So now we need to use all of our symbols now. So the inverse Laplace of f, that equals the inverse of 3 over s plus 3 plus 4 over s squared plus 3. Okay, now we can break these two apart and deal with them individually. So just continuing down from here, we've got the inverse Laplace now of 3 over s plus 3 plus the inverse Laplace of 4 over s squared plus 3. Okay, so now what I want to do is take these constants out, and let's do that on the next line. So now we've got 3 times the inverse Laplace, now 1 over s plus 3. So now that's looking good from our table of Laplace inverse transforms. And then bring the 4 out of this one, and then we've got the inverse Laplace of 1 over s squared plus 3. Now that's looking close to what we want. Well, I think the stuff we could do with that. Now this one here, 1 over s plus 3. Now 1 over s plus 3, what we can write that as 1 over s minus 3. Now we know an inverse Laplace, so inverse Laplace of 1 over s minus a, that equals e to the at. So therefore our inverse Laplace of this one will give us an a value of minus 3, hence this value here. So this one, we can take care of that straight away. So that is now 3, we'll be multiplying it, and e to the minus 3t. So that's been transformed already, so that's taken care of. Now what we want to do is have a look at this one. Now with an s squared plus sign here, what we're looking for here is the inverse Laplace of a over s squared plus a squared, that equals sine of at. Now here we've got a 3, here we've just got a 1. Now if we had the square root of 3 in the top, then we could have straight away a version of sine in our inverse Laplace. So let's get a square root of 3 in the top there. So now I'm going to write that as 4 times the inverse Laplace of square root of 3 over s squared plus 3. Now that's all well and good, but square root of 3 is not the same as that. But what we can do is, as we did here, we took the 4 out. If you've got a square root of 3 and then divide everything by square root of 3, we then even out this and it still becomes a net value of 1. So I can now write this as 4 over root 3. Okay, now here s squared plus 3, or a, if that's 3 and we've got square root of 3, For this, we've got a equals square root of 3. Hence, we've got square root of 3 divided by s squared plus square root of 3 squared. So now our inverse Laplace transform of this we can rewrite. So I'll come to this one in a minute. This one here now, we've got 4 over root 3. That's already taken care of. That's our coefficient. Now the inverse Laplace of this will now become sine of a times parameter t, or t variable, whatever you want to call it. So square root of 3 will be our a. So now we've got sine of square root of 3 times t. So therefore we've got 3 e to the minus 3t. I'm going to write that as 3 over, now I've got e to the 3t in my denominator. That's with a plus sign here. So now I'm going to rewrite this for my final answer, 3 over e to the 3t plus 4 over root 3, and then sine root 3 of t on the top. So now I'm going to write 4 sine, and then I write that as t root 3. That's the way I prefer to write those kind of things. And that I'm going to declare as my answer to this complicated looking function here. We end up with this 3 over e to the 3t plus 4 root 3 sine t root 3. Okay.